Good day to our fellow friends and lecturer. We are from Group 19. So our topic today is mathematical fallacies and invalid agreement. So in this presentation, we aim to teach you something we might not completely know about how hidden logical error and distort mathematical reasoning. So before we dive into the concept, let me introduce our group member. So we have Tan Xin Tian and Nur Farisha Najwa and also Muhammad Hafizuddin. So first, let's define what is mathematical fallacy. So a mathematical fallacy is a proof of argument that appears completely correct on a surface but contains a hidden mistake. It has four main characters, which is it appears logically valid at first glance. Second, it contains an incorrect step somewhere in the process. Third, it produces completely false conclusion. And finally, it can easily mislead people if it is not carefully examined. Can mathematics prove 2 equal to 1? So why do even smart people get fooled by this error, and how this related to logical argument? To explain this further, I will pass the floor to our next presenter, which is Tan.
So these are the topics relationship with our logic and set theory course, which is the chapter 2 logic, chapter 4 arguments, and also chapter 5 about proof methods. Now we are go on to the valid and invalid arguments. Here are the examples of valid arguments, which the premise 1 talk about if a student passes all courses, then the student can graduate. Premise 2 are Sarah passed all courses, and the conclusion is Sarah can graduate. This is an invalid argument which shows the symbolic form P implies Q, then Q, therefore Q. So it using the modulus ponens rules, so the argument is valid.
So now that we have looked at what makes an argument invalid, let's analyze this specific scenario. Premise 1, if a student pass all courses, then the student can graduate. Premise 2, Sarah can graduate. And the conclusion is Sarah passed all courses. Why this argument is invalid? So Sarah might receive a credit transfer, be exempted from a course, and complete the equivalent requirements. So the conclusion does not necessarily follow. Many invalid arguments appear reasonable because people confuse correlation with logical implication. Example, if a person studies hard, they may get an A. Ali studies hard. Therefore, Ali gets an A. This sounds reasonable. However, studying hard does not guarantee an A. The conclusion is not logically certain.
So let's continue for the proof methods. The first method of the proof method is direct proof. In direct proof, we assume the premise P is true and then use logical step. Definition and previously proven theorems to directly shows that the conclusion Q must also be true. So let's look for the example. The statement is if n is an odd integer, then n square is an odd integer. We need to assume P, so assume n is an odd integer. By definition, an odd integer can be written as n equal to k plus 1, where k is an integer. N square equal to 2k plus 1 square. So we expand the square, and then we got n square equal to 4k square plus 4k plus 1. And then we factorize 2, so we got 2k square plus 2k plus 1. The conclusion is, since k is an integer, so n is also integer. The statement is proof. So the next is, if x and y are odd integer, then x, y is an odd integer. Assume p is true. So by definition, we know that 2k plus 1 is odd for some integer. Y equal to 2n plus 1, where n is an integer. X and y equal to 2m plus 1, 2n plus 1. So we expand 4mn plus 2n plus 1. So we factorize 2mn plus n plus 1. So let k equal to 2m plus n. Therefore, we got xy equal to 2k plus 1 is an odd integer. So the next is x plus y is an even integer. So assume p is true. Let's x and y be two even integer. By definition, we know that 2k is even integer. For some integer k, x equal to 2m, where m is an integer, y equal to 2m, where n is an integer. X plus y equal to 2m plus 2n. X plus y equal to 2m plus n. We factorize 2. Let k equal to m plus n. So we got that x plus y equal to 2k is an even integer.
Correction between proof methods and mathematical fallacies. So the proof method helps mathematicians verify statements. It occurs when proof methods are used incorrectly. It is because a small mistake can invalidate an entire proof. Understanding proof methods help us detect fallacies. Now I will go on to the contrapositive part. Sometimes a direct proof is too difficult to construct since a conditional statement P implies Q is logically equivalent to its contrapositive, not Q implies not P. We can prove the statement by assuming the conclusion is false, which is not Q, that showing the premise must therefore also be false, which is not P. Here is one of the example, given that if n is not an even integer, means n is odd, then n squared is not an even integer, means n squared is odd. First of all, we assume that n is not an odd integer, which is n equal to 2k plus 1. Using the same direct proof algebra, n squared equal to 2m plus n squared. So we can factorize the 2 out, become 2 in bracket 2k squared plus 2k close bracket plus 1. So our conclusion will get not p, because n squared is written in form of 2m plus 1, n squared is an odd integer. Since we successfully proved not q implies not p, then p implies q is automatically true. About the contradiction, to prove a statement P is true using contradiction, we begin by assuming the statement is false, not P. Then progress through logical deduction until reach an impossible or contradictory result, which such as 1 equal to 0 or finding an integer that is both even and odd. This proves our initial assumption of falsehood was impossible, meaning the original statement must be true.
So, for the example, the statement square root 2 is irrational. Assumption of negation, not P. Assume square root 2 is rational. This means it can be written as a fraction in its simple form. Square root 2 equal to A over B, where A and B are integers with no common factors. To solve this equation, we need to square both sides. 2 equal to A square over B square implies A square equal to 2B square. This means A square must be an even number, which implies A is an even number. Let A equal to 2K. Substitute A equal to 2K back into the equation. 2K square equal to 2B square, and 4K square equal to 2B square. 2K square equal to B square. This means B square must also be an even number, which implies B is an even number. For the contradiction, if both A and B are even, they both share a common factor of 2. This flatly contradicts our initial rule that the fraction A over B was in its simplest form with no common factors. For the conclusion, the assumption that square root 2 is rational leads to an impossible contradiction. Therefore, square root 2 must be irrational.
Okay, thank you, Hafiz. Okay, so let's move for the quiz sections to test our logical. So, the first question is, if a student studies hard, they will pass the exam. Alex passed the exam. Therefore, Alex studied hard. In symbolic form, premise 1 is P implies Q. If you study hard, then you will pass. Premise 2, Q, you pass. Conclusion, P, therefore you study hard. The question is this argument valid or invalid? So the answer is invalid. Even though the premise sounds convincing, the conclusion does not logically have to follow. While studying hard guarantees passing, which is P implies Q. Passing the exam, Q, could happen for the other reason. Perhaps the exam was exceptionally easy, or Alex guessed all the answer right.
So for the second question, given if n squared is an even integer, then n is an even integer. Prove this using contrapositive. So what is your very first assumption? Given four options that A, assume n squared is an odd integer, B, n is an odd integer, C, n is an even integer, and D, n squared is an even integer. So the answer is B, assume n is an odd integer. To prove a conditional statement P implies Q using contrapositive, we prove its logical equivalent not Q implies not P. Since our conclusion Q is n is even, we must negate it, become not Q, which means we assume n is not even, which n is odd.
So for the third question, statement there is no largest prime number. By using proof by contradiction, what statement do you initially assume to be true? For A, assume there is a largest prime number. B, assume there is no smallest prime number. C, assume all numbers are prime. And D, assume prime numbers do not exist. So the answer is A, assume there is a largest prime number. To prove a statement P by contradiction, we must start by assuming its exact negation P is true. Just like we assume square root 2 is rational to prove it is irrational. Here, we assume a largest prime does exist. So that's all for our presentation.
Thank you.
Thank you.